Starlight leaves its source and does not stop. It spreads outward in every direction at once, thinning as it goes, reaching farther and farther into the dark until the dark is all there is, and the light has become something closer to memory than warmth. At a certain distance from any given star, that light is enough to warm a rocky surface. At a closer distance, it is too much. At a greater distance, not enough. Between those two thresholds, in the band of space where the energy arrives in the right amount, there is the possibility of something specific and rare. There is the possibility of water that neither boils away nor locks itself permanently into ice, but rests on the surface of a world and stays. The spreading of starlight follows a rule that never bends. Every time the distance from a star doubles, the light that arrives at that distance falls to 1/4 of what it was, not 1/2, 1/4. This is because the energy that left the star is being spread over a larger and larger sphere as it travels, and the surface area of a sphere grows with the square of its radius. A planet twice as far from a star as another planet receives not half the warmth, but 1/4. A planet 3 times as far receives 1/9. The fall-off is steep and steady and exact, and it is from this single physical fact that the entire concept of the habitable zone grows. The word habitable is careful, but it does not mean pleasant or welcoming, or even survivable by any organism anyone has ever met. It means in this specific and bounded scientific sense that liquid water could persist on the surface of a world. That one property, the presence of liquid water at the surface, is the threshold the zone is drawn around, and the threshold was chosen because of what water does, and what nothing else yet found has managed to replicate. Water is a solvent of exceptional reach. In liquid form, it pulls apart other molecules and holds their pieces in suspension. It carries ions and organic compounds from one place to another within the structures of living things. It forms the medium in which the chemistry of every living cell on Earth takes place, and it is the only medium in which life, as presently understood, has been confirmed to function. There are other liquids, there are other possible chemistries, in principle, and scientists have imagined them with care and taken them seriously. But liquid water on a planetary surface under atmospheric pressure is the one place where life is known to have existed, and so it became the one property that early theorists built their zone around. It was not a declaration that water was the only possibility. It was a decision to begin with what was known. That decision was made formally in a year when the first telescopes capable of finding planets around other stars did not yet exist and would not exist for decades. It was made on paper in the language of physics and planetary science by a man who was thinking about a question that had no practical method of investigation at the time, but that seemed worth asking precisely because it was so large. His name was Huang Sushu, a Chinese-American astrophysicist, and in 1959 he published a paper in the publications of the Astronomical Society of the Pacific that drew a ring around the concept of where life might be possible and gave it a name. The zone he defined was the region around a star where a planet could, in principle, maintain liquid water on its surface. Warm enough, not too warm.
The language was simple. The implications were vast.
The paper rested on a printed page with equations running in neat small lines across it, the kind of page that does not announce its own importance. Huang was not building toward a discovery he could demonstrate in a laboratory. He was doing something quieter. He was making a map for a territory that might not even exist, and placing on that map the single condition that seemed most likely to matter. Around stars in the sky above him, Planets might be circling at distances that put them in the range he described. He could not see them, but he could say where they would have to be to hold liquid water, and that was enough to begin. The distance from a star that defines the zone depends almost entirely on how bright the star is. A dim star, one that puts out only a fraction of the sun's energy, has a habitable zone that sits much closer in, where the weakened light can still deliver enough warmth. A bright star, one that floods its surroundings with energy, has a habitable zone that extends much farther out, because a planet has to be farther away before the flux drops to a tolerable level. The zone is not fixed in space. It is a function of the star it surrounds, shaped entirely by luminosity, and luminosity alone sets its position before any other factor is introduced. In those early years, the habitable zone was this, and not much more. A ring, a distance range, a place where the numbers said liquid water was possible. It was a starting point rather than a conclusion, and those who built on it knew that. Huang himself described it in terms that acknowledged its incompleteness. He was identifying a necessary condition, not a sufficient one. A planet in the zone was a planet where one requirement had been met. What other requirements existed, and how they interacted, was work for the years ahead. The years ahead came, and they brought refinements. In 1964, Stephen Dole published a study that considered not only how much light a planet received from its star, but also how much of that light the planet reflected back into space before it could warm the surface. A planet covered in ice or bright cloud reflects a large fraction of the incoming energy. A planet covered in dark ocean or dark rock absorbs most of it. The proportion reflected is called albedo, and it matters enormously for the surface temperature. A world with high albedo can sit in the zone and still be cold because it is sending most of the warmth away before it can do any work. A world with low albedo can sit nearer the outer edge and still maintain enough surface temperature for liquid water. Dole's work folded this complexity into the picture, and the zone that emerged was narrower than what Huang had drawn. Then the eccentricity of orbits entered the picture. A planet does not have to circle its star in a perfect ring at constant distance. Most planets travel in ellipses, paths that bring them closer at some points in their orbit and push them farther away at others. A planet on a highly elliptical orbit might spend part of its year within the zone and part of its year outside it. Whether that planet could maintain liquid water would depend on how long it spent in each region and on how quickly the surface could heat and cool. An orbit shaped like a stretched oval is different from a circle, and the difference has consequences for habitability that Dole began to map. Atmospheric stability was another consideration. A planet with an atmosphere can use that atmosphere to trap warmth at the surface through the same mechanism that makes a greenhouse warmer than the open air. Without an atmosphere, even a planet at the right distance from its star might have a surface temperature far too cold for liquid water, because all the warmth that arrived in the daytime would radiate back into space during the night, with nothing to hold it in. The atmosphere is not an ornament. It is a component of the thermal system that determines whether the zone's promise can be fulfilled. Dole recognized this and worked it into his estimates, and his estimates were narrower still. By 1979, Michael Hart had produced computational models that carried these refinements further. Hart ran simulations of planetary atmospheres and their responses to stellar flux, and what he found made the habitable zone look very small. His models suggested that the zone around the sun, accounting for all the feedbacks between the surface, the atmosphere, and incoming radiation, was narrower than even Dole had estimated. The precise figures from Hart's work were later revised, but the intellectual move he made was important. He had shown that the zone was not simply a question of distance, it was a question of how multiple systems interacted, and those interactions could tighten the livable range substantially. The landscape that Hart's models described was one of competing pressures. A planet slightly too close to its star receives slightly more energy than it would at a safer distance, and a surface warming begins. As the surface warms, more water evaporates into the atmosphere. Water vapor is itself a greenhouse gas, trapping additional heat. The additional heat causes more evaporation. The additional evaporation causes more warming. The cycle feeds itself. If it progresses far enough, the planet's oceans are gone, lifted into the sky as vapor, and then carried slowly away into space by the solar wind. The surface that remains is dry and airless and scorched. This spiral of warming and water loss is the fate that defines the inner boundary of the habitable zone, the place where the distance from the star becomes too small, the flux too high, and the feedback loop cannot be stopped. On the other side, the outer boundary is governed by a different kind of limit. A planet far from its star receives little energy. To compensate, an atmosphere loaded with carbon dioxide can build up over time through volcanic outgassing, trapping the small amount of warmth that does arrive. Carbon dioxide is an effective greenhouse gas, and a thick blanket of it can warm a surface that would otherwise be far too cold. But there is a limit to how much this compensation can help. As the concentration of carbon dioxide in the atmosphere continues to rise, the gas begins to condense into clouds and crystals in the upper atmosphere at the low temperatures prevailing there. Those clouds and crystals are bright. They reflect incoming starlight back into space before it reaches the surface, cooling the planet rather than warming it. The carbon dioxide that was warming the planet becomes the agent of its further cooling. The addition of more greenhouse gas past a certain threshold no longer helps. The outer boundary of the zone has been reached, and beyond it, a planet's climate cannot be stabilized by any greenhouse mechanism alone. These two limits, the runaway warming at the inner edge and the collapse of the greenhouse effect at the outer edge, define the zone not as a line, but as a range. Within the range, the conditions for liquid surface water can be met. Outside it in either direction, those conditions break down in different ways for different physical reasons. The range is real, it is derived from physics, and it is the frame within which all subsequent habitable zone science has been built. The 1993 work of James Casting and his colleagues at Pennsylvania State University was the moment when all of these threads were drawn into a single rigorous framework. Casting and his team built detailed climate models that incorporated atmospheric physics, photochemistry, and the interactions between surface water, atmospheric gases, and stellar radiation. Their models produced specific distances for the inner and outer edges of the habitable zone around stars of different types, with numerical values grounded in physical mechanisms that could be tested and revised as new data arrived. The habitable zone as a scientific tool, rather than a thought experiment, emerged from that work. It became something that could be applied to real stellar observations and used to evaluate whether specific planets, once found, were candidates worth investigating further. The metaphor that had attached itself to the concept by then was not from any scientific paper. It came from folklore, from a story about a child who walked into a house in the woods and found 3 bowls of porridge, 3 chairs, and 3 beds. One of each was too much. One of each was too little. The middle one was just right. The habitable zone had become, in popular understanding, the Goldilocks zone. The name was vivid, and it was useful for a first introduction. Scientists used it too, freely, because it communicated the essential idea in an instant. Not too hot, not too cold, just right. The scientists who used it also knew its limits, and some of them were careful to say so. Goldilocks found one right answer in a house with three options. The habitable zone is not a house with three options. The habitable zone is not a house with. It is a region in space where one condition is satisfied, and that condition is necessary but not sufficient. And the story of whether a particular world is actually habitable involves many other chapters that the metaphor cannot reach. The porridge in the story stayed the same temperature while the child was deciding. The conditions inside a real planetary system evolve across billions of years. The star brightens, the planet's atmosphere changes composition. The volcanic activity that replenishes the carbon dioxide in the atmosphere may wane. The magnetic field that shields the surface from stellar radiation may weaken. None of these things are in the story of the three bears. The metaphor is a door. It is not the room behind the door. It is not the room behind the door. Beyond the metaphor, the zone rests on the specific and peculiar properties of water itself, and it is worth resting there for a moment because those properties are genuinely strange. Most substances are densest in their solid form. Water is denser as a liquid than as ice. This is why ice floats. If ice sank, the freezing of a lake would proceed from the bottom upward, and deep lakes in cold climates would freeze solid through their entire depth every winter, sterilizing whatever lived in them. Because ice floats, it forms a surface layer that insulates the liquid water beneath it, and life persists in the depths. This one property of water has consequences for the survival of aquatic life on any cold world where water exists. Water also has an unusually high capacity for absorbing heat before its temperature rises, which makes it an excellent buffer against rapid temperature swings. Oceans warm slowly in summer and cool slowly in winter, moderating the temperature swings that land-covered surfaces experience. A planet with a surface largely covered by liquid water is a planet with a more stable climate than one without it, because the water itself is working to hold conditions steady. The very presence of the ocean that defines habitability also helps maintain the conditions that allow the ocean to persist. There is a self-reinforcing quality to a water-covered world that Hardin Casting both recognized and built into their models. The solvent properties of liquid water are a different category of remarkable. Water pulls apart ionic compounds with an efficiency that few other liquids can match. Sodium and chloride, iron and sulfur, phosphate and calcium, water draws these apart and holds them in solution where they are mobile, where they can encounter each other and react, where the chemistry of living processes can proceed at the rates and with the selectivity that biology requires. A living cell is, among other things, a bag of water in which an enormous number of reactions are taking place simultaneously, each one made possible by the solvent in which the reacting molecules are suspended. Remove the water, and the chemistry stops. Freeze the water solid, and the molecules can no longer move to meet each other. Boil the water away, and the medium that carries the chemistry no longer exists. Liquid water is not just a temperature indicator, it is the environment in which life, as known, operates. This is why the definition of the habitable zone is built on water rather than on temperature alone, and why temperature matters only insofar as it governs the state of water. A surface at 10 degrees below freezing might not seem dramatically different from a surface at 5 degrees above it, but in terms of what can happen there, the difference is complete. Below the freezing point, the water is locked and the chemistry it enables is stopped. Above it, the water flows and the chemistry can run. The habitable zone is not really about temperature, it is about the phase of water, and temperature is the variable that determines the phase. The phase diagram of water, the map that shows under what combinations of temperature and pressure water exists as solid, liquid, or gas, traces the precise conditions under which an ocean can persist across geological time. At low pressure and low temperature, water is ice. At low pressure and high temperature, water is vapor. At intermediate conditions, in the range where temperature and pressure both fall within bounds that can be maintained on a planetary surface, water is liquid. The boundaries of that region on the phase diagram are not arbitrary. They follow from the physics of molecular bonding and thermal energy, and they set the physical target that the habitable zone is trying to enclose. A planet is in the zone if its surface conditions place it inside the liquid region of that diagram. The zone is, in the end, a spatial projection of a thermodynamic boundary. All of this precision rests on an assumption that is itself a hypothesis rather than a certainty. The assumption that liquid water is necessary for life, or at least that life without liquid water has not yet been found and therefore cannot yet be counted in any assessment of habitability. This assumption is the honest anchor of the concept. It is not a claim that water is the only possible medium for chemistry complex enough to be called biology. It is a claim that water is the medium in which the only known life exists, and that searching for liquid water is therefore the most defensible first step in searching for life beyond Earth. The concept, from its 1959 beginnings through its computational refinements in the following decades, is precisely this, a first step made as honestly and rigorously as the available knowledge allowed. Huang drew the map in the terms he had. Dole refined it with albedo and eccentricity. Hart narrowed it with atmospheric feedbacks and computational models. Casting and his colleagues grounded it in detailed physical chemistry. Each step added precision, and each step also added complexity, and the complexity revealed that the zone was not a simple answer, but a structured beginning. A planet can sit at exactly the right distance from exactly the right kind of star and still be uninhabitable. Its atmosphere might be too thin to hold pressure, and the water that would otherwise pool on its surface sublimates directly into vapor. Its atmosphere might be too thick, trapping so much heat that the surface temperature is far above the point where water boils, the way Venus, sitting on the inner edge of the sun's habitable zone, by some estimates, has a surface hot enough to melt lead, its oceans gone for billions of years, its sky a dense and acidic overcast that lets nothing out. Its orbit might be too eccentric, swinging it through the zone in seasons too brief for a stable surface to develop. Its star might be too active, stripping away atmospheric gases with energetic particles and radiation faster than any geological process can replenish them. The zone is a necessary condition. Necessary conditions are not guarantees. They are requirements that must be met before other requirements can even be asked about, and the fact that a world meets the first requirement is only the beginning of the inquiry into whether it meets all the others. For a long time, the inquiry was entirely theoretical. There were no confirmed planets around other stars. There were no methods precise enough to detect them. The habitable zone was a concept in search of objects to apply it to, and the objects existed only as abstractions in stellar catalogs, stars at known distances, with known luminosities, around which planets were presumed to be possible but could not be observed. The zone was a prediction. It was a frame sitting empty, waiting for something to enter it. The frame was built carefully because the people who built it expected it to matter eventually. The universe is not empty. Every star is a candidate. There are more stars in the Milky Way than there are grains of sand on all of Earth's beaches, and each of them pours energy outward in every direction, and around most of them, the physics that governs the habitable zone applies. The inverse square dimming of stellar flux, the greenhouse warming of atmospheres, the phase boundaries of water, these are not sun-specific phenomena, they are universal. Wherever in the galaxy a rocky planet circles a star at the right distance, the same physics applies, and the same question can be asked. That universality is what made the habitable zone concept worth developing even when no exoplanet had yet been confirmed. It would be wrong to say that Huang Sushu, sitting down in 1959 to write a paper for a professional astronomical journal, knew with any certainty that his framework would one day be applied to real candidate worlds. He could not have known. The tools did not exist. But he was working within a tradition of science that builds its frameworks before its observations, or builds them alongside them, in the understanding that the map and the territory develop together, and neither is complete without the other. A concept grounded in water, built on the inverse square law, refined by atmospheric physics, and bounded by the phase diagram of the most common liquid on Earth. This concept was the best available frame for the question of where else life might find the conditions it seems to need. It remains the best available first frame. It is not the whole picture. The scientists who use it know this. They use it because a first frame, honestly built, is worth more than no frame at all, and because the conversation about its limits is itself a productive conversation, one that has already expanded the picture in important ways. A star hangs in the dark. Its light spreads outward in every direction in widening rings that grow fainter with distance. At a certain distance from that star, the light is neither too much nor too little, and the question of what might be possible there opens quietly, without urgency, into the long darkness surrounding it. The boundary is not a wall, it is a suggestion. It is the place where one condition for one kind of life might be met, drawn on a map that is honest about what it shows and honest about what it leaves out. That honesty is where the science begins. The zone was never meant to be a final answer. It was meant to be a question asked carefully in a region of space where the question seemed worth asking. It draws a line around the idea of where, given what is known, the conditions for life as understood might be met. It draws that line with precision derived from physics, with caveats derived from humility, and with the understanding that every precise line drawn in science is a line that future measurements will either confirm or revise or dissolve entirely into something more nuanced. A first step is still a step, and the step was taken in the right direction, outward, into the dark, toward the places where starlight still arrives with enough warmth to keep water liquid on the surface of a world, if one happens to be there, turning slowly in the quiet of its orbit, beneath a sky it has never been asked to explain. The concept that grew from a 1959 paper into a working tool for planetary science is, in the end, a scientific starting point shaped around the one medium in which life is confirmed to exist. It is water-centric because life as known is water-dependent. It is stellar flux-centric because stellar flux is what determines the surface temperature of a rocky planet in the absence of other heat sources. It is approximate because the real conditions on any given world depend on more variables than any zone calculation can contain, and it remains open, genuinely open, not rhetorically open to revision and extension as the science that surrounds it continues to develop. That openness is not a weakness. It is the quality that makes the concept useful rather than brittle, a definition that cannot be questioned, cannot be refined, a frame that cannot be extended, cannot accommodate new knowledge. The habitable zone holds its boundaries loosely enough that when a world is found that challenges those boundaries, the challenge becomes data rather than contradiction, and the picture that emerges from the challenge is always more detailed and more accurate than the one that preceded it. The zone is a living frame, built on physics, applied with care, and held with the kind of quiet intellectual confidence that does not need to be final to be worth building on. Out in the dark beyond this planet, around stars that will not be visited in any human lifetime, there are distances from those stars where the inverse square law brings the light down to the level where water stays liquid. The rocks there, if rocks exist there, are neither scorched nor frozen. The air there, if air exists there, may be holding a surface in the narrow thermal range that the phase boundaries of water define. Whether anything lives in those conditions or could is a question the zone alone cannot answer. But it is the question, and the zone is where it begins, in the quiet dimming light at exactly the right distance from a star, where neither the cold nor the heat has won, and where the possibility of something else entirely rests, suspended in the middle distance. Over a warming ocean, in the early life of a world still finding its balance, water rises from the surface in a slow and steady climb. The heat comes from above. It presses down in long invisible waves, and the ocean answers by releasing itself, molecule by molecule, upward into the air. Steam thickens above the water, the sky holds more of it each hour, and in that slow, accumulating rise, the first step of a mechanism begins, one that, left unchecked, leads a world from warmth to ruin. This is where the inner edge of the habitable zone begins, not in a diagram, not in an equation written on paper in a quiet office. It begins here on the surface of a warming world, where water is rising and the sky is filling, and the balance between warmth and life is starting to tip. The runaway greenhouse effect is what scientists call the process that defines how close a planet can orbit its star before the presence of liquid water becomes impossible. It is not an instant catastrophe. It is a slow feedback, one thing following the next, each step making the next step easier. The star delivers heat to the planetary surface. The surface warms. Warming drives evaporation. Water vapor rises into the atmosphere. And water vapor, like carbon dioxide, is a greenhouse gas. It traps the heat that the surface radiates back upward, preventing it from escaping into space. With more heat trapped, the surface warms a little more. More water evaporates. More vapor accumulates. More heat is held. The surface warms again. The cycle tightens, turn by turn, until the oceans have given themselves entirely to the sky, and the sky itself is a thick, scalding envelope of steam. The liquid water that made life possible is gone. It is not frozen. It is not hidden. It is simply no longer a liquid. From a sun-like star, the point at which this cycle becomes self-sustaining lies at roughly 9/10 of the distance from our sun to Earth. Inside that distance, under that level of stellar heat, a planet with water cannot hold it. The water rises and does not come back down. The ocean becomes an atmosphere, and the atmosphere becomes a trap. That boundary, drawn at roughly 19/20ths the distance of Earth from the sun, marks the closest edge of what models call the conservative habitable zone. The outer edge is governed by a different mechanism, where the inner boundary is defined by too much heat and the runaway rise of vapor. The outer boundary is shaped by a gas that does everything right until it does one thing that undoes it all. That gas is carbon dioxide. On a cold world far from its star, the surface radiates little heat. The planet needs an insulating blanket of atmosphere to stay warm. Carbon dioxide provides that blanket. It is an excellent greenhouse gas, At the concentrations found in planetary atmospheres, it absorbs heat radiating from the surface and redirects much of it back downward. A planet that is slightly too cold can compensate, at least in part, by accumulating carbon dioxide over time. And this is not purely theoretical. The carbonate-silicate cycle, the slow geological exchange between rock, ocean, and atmosphere, tends to build up atmospheric carbon dioxide when a planet cools, because cooler temperatures reduce rainfall, reduce weathering of rock, and allow volcanic carbon dioxide to accumulate without being drawn back down. In this way, a planet has a natural tendency to keep itself warm, cool down, and the atmosphere thickens. Thick atmosphere, and the warming resumes. This cycle has limits. At some distance from the star, even the thickest plausible carbon dioxide atmosphere cannot compensate for the loss of stellar heat. The planet simply does not receive enough energy from its star for any greenhouse blanket to make up the difference. That is one constraint. The other is stranger and less obvious. Carbon dioxide, like water, undergoes phase transitions. At low enough temperatures and high enough concentrations, it condenses, and on the night side of a cold planet, or in the upper reaches of a cold atmosphere, that condensation can begin to happen. Carbon dioxide clouds form, and carbon dioxide clouds, unlike the clear gas below them, are reflective. They send incoming starlight back into space before it can reach the surface and warm the planet. This is the maximum greenhouse limit, the point at which carbon dioxide, by condensing and forming reflective clouds, begins to do the opposite of warming. The atmosphere that was supposed to save the planet from the cold instead increases the cold. More cold produces more condensation. More condensation produces more clouds. More clouds reflect more light. The planet cools further. The mechanism that was supposed to keep a world habitable inverts itself, and past a certain distance from the star, no amount of atmospheric carbon dioxide can reverse the outcome. In conservative models, this outer limit for a sun-like star lies at roughly 1 2/3 the distance of Earth from the Sun. Inside that range and outside the inner boundary, liquid water is at least plausible at the surface, under the right atmospheric and geological conditions. Outside that range, even the most generous physics cannot hold an ocean open under the sky. These two boundaries, the inner moist greenhouse limit and the outer maximum greenhouse limit, form what scientists call the conservative habitable zone. It is conservative because it relies only on mechanisms that are well understood and well modeled. It does not assume exceptional planetary properties. It does not assume active volcanism of a particular rate, or an ocean of a particular depth, or a magnetic field of a particular strength. It assumes a rocky planet with a water ocean and a carbon dioxide atmosphere, and it asks simply, at what distances can that planet keep its ocean in a liquid state? The question sounds simple. The answer required decades of increasingly careful work, and the physics that underlies the boundaries is still being refined. In 2013, a physicist named Ravi Kopparapu and a group of colleagues published a set of revised habitable zone calculations that have since become the standard reference for this field. The revision turned on a technical but consequential update, better spectroscopic data. The original calculations used older measurements of how water vapor and carbon dioxide absorb infrared light at different wavelengths. By the early 2010, the databases that cataloged those absorption properties, gathered from laboratory measurements and updated continuously over decades, had improved substantially. Water vapor in particular absorbs heat across a broader range of wavelengths than earlier models had captured, And that difference matters when calculating precisely how much of a planet's outgoing heat gets trapped at various atmospheric compositions and temperatures. When Kaparapu and colleagues recalculated the habitable zone boundaries using the updated absorption data, the inner edge moved slightly inward, closer to the sun, and the outer edge moved slightly outward, modestly widening the zone. One of the notable outcomes was that Earth itself, in the revised calculations, sits closer to the inner edge of the conservative habitable zone than earlier estimates had suggested. Not dangerously close, not outside the zone, but closer than the older numbers implied, in a way that shifted how scientists think about Earth's own climate history and the margins within which our world has maintained its oceans over 4 billion years. These calculations now serve as the working reference whenever a new planet is found, and scientists want to know whether it orbits in a region where water might be liquid on its surface. The boundaries are not certainties, they are physically grounded estimates. A planet inside the zone may have no water at all. A planet just outside the zone may have some means of retaining warmth that the model does not account for. What the zone offers is a starting framework, a way of organizing the vast catalog of worlds being found around other stars, and asking which ones are worth examining more carefully. The shape of a habitable zone is not fixed across all stars. It changes completely depending on the star at its center, and the ways it changes are deep and various. A dim red star, what astronomers call an M-dwarf, burns much cooler than the sun. It releases far less energy per second, and what energy it does release peaks at longer wavelengths, well into the infrared. Its habitable zone sits very close to the stellar surface. The distances involved are a fraction of what they are around the sun. A planet in the habitable zone of a cool red dwarf might orbit at less than a tenth the distance of Earth from the sun, completing its year in a matter of weeks, every sitting so close to its star that the gravitational tide from the star has had billions of years to lock the planet's rotation to its orbit. That tidal locking is one of the defining characteristics of habitable zone planets around dim stars. When a planet orbits close enough to a massive body, the gravitational pull on the near side of the planet is slightly stronger than the pull on the far side. Over time, this differential force slows the planet's spin until one face permanently points toward the star and the other permanently faces away. The result is a world of permanent day and permanent night. On the lit side, the star hangs fixed in the sky, pouring heat into a single hemisphere without pause. On the dark side, temperatures plunge far below freezing and stay there. The terminator line between these two hemispheres traces a narrow band where the star hangs perpetually on the horizon and where temperatures settle somewhere between the scorched and the frozen. Whether such a world can remain habitable is a question that depends heavily on its atmosphere. If the atmosphere is thin or absent, the heat on the day side cannot travel to the night side, and the day side grows extreme, perhaps too hot for water at the surface, while the night side becomes cold enough to freeze out atmospheric gases entirely. But if the atmosphere is thick enough, the dynamics change. Winds carry heat from the day hemisphere toward the night hemisphere. The terminator warms somewhat. The night side, though still cold, does not collapse into the absolute freeze that would steal gases away. The planet remains capable of sustaining something like a global atmospheric circulation, and with it, perhaps, the conditions for liquid water somewhere along the terminator or on the warmer reaches of the day side. The question of whether such atmospheres can persist is one of the more active areas of research in this field. M-dwarf planets face an additional challenge from the stars themselves. Red dwarf stars are not quiet. They produce powerful and frequent bursts of radiation, stellar flares that release energy across ultraviolet and X ray wavelengths in intense pulses that can be many times stronger than anything the Sun sends toward Earth. A planet orbiting close to an active red dwarf receives not just steady light and heat, but periodic radiation storms. What those storms do to a planet's atmosphere over millions and billions of years is not fully settled. The most energetic radiation can strip gas from the upper atmosphere. Solar wind from a flaring star can erode the atmosphere directly, particularly if the planet lacks a strong magnetic field to deflect it. Over geological time, a planet that starts with a thick protective atmosphere may gradually lose enough of it that the protective effect weakens, which makes further loss easier, which weakens the protection further. At the other end of the stellar spectrum, hot bright stars of the type astronomers call F-type stretch the habitable zone far outward. A planet that receives enough heat to keep liquid water on its surface while orbiting a luminous F star might sit at a distance of 1.5 times Earth's distance from the Sun or more. The habitable zone around such a star is wide, in the sense that the range of distances within it is large. But these stars have a different complication. They are shorter lived than the Sun, burning through their fuel more rapidly. A star significantly more luminous than the Sun may remain on the main sequence for only a few billion years, compared to the Sun's roughly 10 billion years. Whether that is long enough for complex life to emerge and flourish is an open question that bears on how we weight such systems in the search for inhabited worlds. The Sun itself occupies a middle ground. It is a G-type star of moderate mass and luminosity, burning steadily for a time span long enough that life on Earth has had 4 billion years to develop from its simplest forms to its most complex. The habitable zone around the Sun is well studied, partly because Earth sits within it and provides a living demonstration of what habitable zone residents can produce. But even the Sun is not static. Over its lifetime, the Sun has grown gradually more luminous. Early in the solar system's history, the Sun was significantly dimmer than it is today, roughly 3/10 less luminous than its current output, by the best available estimates. This creates a puzzle that planetary scientists have thought about for a long time. If the early Sun was that much dimmer, Earth should have been frozen. The stellar flux it received in its youth was below what current models of planetary atmospheres suggest is necessary to keep the oceans liquid. Yet the geological record and the evidence for early life makes clear that Earth's early surface was not frozen. The oceans were liquid. Life was present. Somehow the early Earth maintained habitable surface conditions, despite receiving less energy than the zone boundaries would predict. Various explanations have been proposed. Higher concentrations of greenhouse gases, methane in particular, in the early atmosphere could account for some of the warming. A different orbital distance, or different albedo, or different cloud behavior could shift the calculations. The puzzle is not resolved, but it is deeply instructive because it illustrates that the habitable zone, as calculated from stellar flux alone, is only part of the picture. Planetary and atmospheric factors matter enormously. The zone marks where habitability is possible, not where it is guaranteed or impossible. The habitable zone around any star also changes over time as the star evolves. As a star ages on the main sequence, its luminosity increases. The zone migrates outward. A planet that sat comfortably within the zone in the early life of the system may eventually find itself inside the inner boundary as the star grows warmer, receiving more heat than its oceans can withstand. Earth faces this fate on a timescale of more than 1 billion years, as the sun's continuing brightening will eventually push the inner edge of the habitable zone past Earth's orbit. In the other direction, a planet that once sat just outside the outer edge of the zone may eventually find itself inside it as the star brightens and the zone expands. Mars may be approaching this condition in the distant future as the sun slowly increases its output. The region that remains within the habitable zone for the entire main sequence lifetime of a star is narrower than the instantaneous habitable zone. Scientists call it the continuously habitable zone. For a star like the Sun, this narrower band excludes the inner and outer portions of the wider zone that are only habitable for part of the star's life. A planet must sit within it from the beginning to the end to remain in habitable zone conditions throughout. The continuously habitable zone is a more stringent criterion, and a planet that meets it has the advantage of long-term stability. The same general conditions persisting across the billions of years that complex life on the evidence of Earth appears to require. Boundaries drawn around a single star represent the simplest case. Many stars are not alone. Binary systems, two stars orbiting a common center of mass, present a different challenge entirely for habitable zone calculations, because the stellar flux a planet receives depends on the positions of two sources at once. A planet might orbit one of the stars in a binary pair, sitting at a stable distance from its primary, while the companion star swings through its own orbit at a greater or lesser distance. The flux from the companion adds to the flux from the primary, and depending on the companion's orbit, that addition can vary considerably over time. A planet in such a system does not receive a steady stream of light from a single direction. It receives a combined illumination that fluctuates as its stars move relative to it, cycling through a range of total stellar flux during each orbital period of the binary pair. Alternatively, a planet might orbit both stars from a wide outer orbit, so distant that both stars appear close together from the planet's surface, their combined light acting as a single source. In such systems, the habitable zone must be calculated from the combined luminosity of the pair, and stable planetary orbits can exist at distances where the gravitational dynamics permit them. There are also orbital configurations that are simply not stable, regions where the competing gravitational pulls of the two stars would perturb a planetary orbit so strongly that the planet could not remain at a consistent distance from either, eliminating any possibility of steady thermal conditions. None of this makes binary systems impossible hosts for habitable planets. The evidence from discovered planetary systems makes clear that orbits around pairs of stars can be stable and long-lived. What it does mean is that applying habitable zone calculations to binary systems requires an additional layer of analysis beyond the simple model developed for isolated stars. The conservative habitable zone and the optimistic habitable zone represent two different philosophies of caution. The conservative zone uses only the well-modeled greenhouse limits. The optimistic zone extends the boundaries using empirical evidence from the solar system's own planets, specifically Venus and Mars. Venus, at roughly 7/10 of Earth's distance from the Sun, now sits well inside the inner boundary of the conservative habitable zone. Its surface temperature is around 465 degrees Celsius, hot enough to melt lead, and its atmosphere is a dense, crushing blanket of carbon dioxide. But Venus was not always this way. Geochemical models and the geological record of the surface suggest that early Venus may have had liquid water on its surface for a period in its deep past, before the runaway greenhouse mechanism completed its work. If Venus once had liquid water oceans, then the inner edge of the habitable zone extends at least to Venus's distance from the Sun, perhaps further. That empirical observation allows the optimistic zone's inner boundary to be drawn closer to the star than the conservative model suggests. Mars, at roughly 1.5 times Earth's distance from the Sun, sits outside the outer boundary of the conservative habitable zone in most models, but the surface of Mars holds the carved signatures of ancient water, river valleys, delta formations, dry lake beds, and minerals that only form in liquid water. Mars had liquid water on its surface, at least episodically, in its early history. If Mars was once habitable, then the outer edge of the habitable zone extends at least to Mars's distance from the Sun. That observation allows the optimistic zone's outer boundary to be drawn further from the star than the conservative model suggests. The optimistic zone is larger. It contains more candidate planets. It is grounded not in theoretical models alone, but in the actual historical behavior of the two planets that bracket Earth in the solar system. But it carries more uncertainty. The conditions that allowed early Mars to have liquid water are not fully understood. The duration and consistency of that early habitability is debated, and the optimistic zone implicitly accepts that a planet can be habitable for a limited period in its history, not necessarily throughout its life. That may be enough time for life to begin. Whether it is enough for life to persist or to leave evidence that distant observers could detect is another matter entirely. Between the conservative and optimistic habitable zones, the number of planets that qualify as potentially interesting roughly doubles. That gap between the two estimates is not a flaw in the science. It is the science working honestly, offering a range that reflects what is known firmly and what is known tentatively, and making the distinction clear so that decisions about which worlds to study first can be made with appropriate calibration. The spectroscopic detail of how stars and atmospheric gases interact at specific wavelengths underlies every boundary calculation. Water vapor absorbs heat most efficiently at certain infrared wavelengths, and carbon dioxide at others. Where those absorption bands are wide and strong, the greenhouse effect operates efficiently, and a smaller amount of the gas can trap a significant amount of heat. Where the bands are narrow or weak, the gas must be present in much higher concentrations to achieve the same effect. The updated databases that Koparapu and colleagues used in their 2013 recalculation contained more accurate measurements of these absorption properties across a wider range of temperatures and pressures than had previously been available, and the differences, while small in any single measurement, accumulated across the full calculation to shift the zone boundaries measurably. This connection between laboratory spectroscopy and habitable zone calculations is one of the less discussed but most important threads in the field. The data being gathered in laboratories on Earth, measurements of how specific molecules at specific temperatures and pressures absorb infrared radiation at specific wavelengths, feeds directly into the models that determine which distant planets are candidates for further study. The precision of the boundary is limited by the precision of those measurements. As the measurements improve, the boundaries shift slightly, and the list of candidate worlds adjusts with them. In a cold planetary sky, at the outer boundary of the zone, something settles. Carbon dioxide, building through long ages of volcanic outgassing and the suppression of the weathering cycle, accumulates layer by slow layer in the atmosphere. For a time, it holds the warmth well enough. The surface remains above freezing. Water remains liquid in the lower lying basins and along the equatorial regions, where stellar light strikes at the most direct angle. The atmosphere does its work, but the star is far. The light arriving at the surface is faint, and at higher latitudes, where the light strikes at shallower angles and the surface radiates heat freely into the dark, the temperature falls below the point at which carbon dioxide remains a gas. Ice crystals of it form in the upper atmosphere, clouds of it gather, and the reflective surface those clouds present to the incoming starlight sends energy back upward before it can warm the surface at all. The same atmosphere that was holding heat now deflects it, not all at once, not in a sudden shift. Slowly, the way all changes at planetary scale proceed, in increments too small to observe across a human lifetime, but unmistakable across the expanse of geological time. The balance between warming and cooling in an atmosphere is never entirely settled. It is a slow negotiation between the energy arriving from the star and the energy the planet manages to retain, conducted through the chemistry of gases and the physics of radiation across timescales longer than anything that has yet happened in human history. Where that negotiation holds, somewhere between the inner edge and the outer edge, somewhere in the narrow range where water neither boils into the sky nor freezes permanently into the rock, an ocean can exist. And where an ocean can exist, the conversation about what else might be possible begins. Drawing the boundaries is an act of calibrated honesty. The inner edge is set where physics says the loss of surface water becomes self-sustaining. The outer edge is set where physics says the warming mechanism inverts itself and can no longer compensate for distance from the star. Between those two lines, the zone is not a guarantee of life. It is a region where the universe has not, by the forces it most reliably deploys, made liquid water impossible. That is all. It is enough. Where a line can be drawn, a search can be organized. Where a search can be organized, worlds can be compared and ranked and examined in order of promise, and the patient accumulation of evidence that constitutes the science of other worlds can proceed. The conservative zone and the optimistic zone differ not in their physics, but in their assumptions about what the boundaries of habitability have already been shown to be. The conservative zone trusts only the calculations. The optimistic zone also trusts the geological record of the two worlds in our own system that sit at the edges of where water has been found. Together they describe not a single line, but a gradient of probability, highest at the center, declining toward the inner and outer edges, falling to low, but not impossible levels at the empirically derived outer margins, and dropping sharply beyond them. That gradient is what the habitable zone actually is. Not a ring, though the diagram shows a ring. Not a yes or no boundary, though the calculation produces a number. A gradient of physical plausibility, centered on the orbital distance where liquid water is most stable, extending outward and inward to where the mechanisms that could sustain it are still credible, and fading beyond those limits into conditions where no realistic combination of atmospheric chemistry and planetary geology could compensate for the stellar environment. Where the zone ends, other questions begin. A planet outside the conservative zone may still have liquid water if its interior is warm enough, if its atmosphere is dense enough with the right gases, if its albedo and cloud cover combine in just the right proportion to hold a temperature that the stellar flux alone would never produce. These are not common conditions, but the universe is old and wide, and rare conditions accumulate at scale. The zone tells us where to look first. It does not tell us where life is impossible. That distinction is small but everything, because the first tells us where to point our instruments, and the second would require a certainty the science has not earned and does not claim. A planet sits in the habitable zone, or it does not, That is a fact about stellar flux and orbital distance. Whether it is habitable is a different question, longer and harder, requiring knowledge of atmosphere and geology and water inventory and magnetic fields and the history of its star. The zone is the starting point. It is not the answer, but starting points matter. Without them, the search has no order, no priorities, no method. The boundary drawn at the point where water vapor rises and does not return is not a final word on life. It is the first word in a longer conversation, written in the language of physics, reaching outward from a warming ocean and a sky that holds too much steam toward the darkness where other oceans wait, and other skies, and other balances between heat and cold that hold water in its liquid and living form. The line drawn at the edge of the zone is drawn there because that is where the physics of water and heat make their most definitive statement. On one side, water is free. On the other side, it is not. The zone is where water is free, where the molecules at the surface can move and dissolve and carry and enable, where the ocean lies open under the sky, still and receiving, holding the light of a distant star across its surface in the long and patient work of a world that has not yet been asked what it might contain. On the surface of a planet that circles a small red star, the sun never rises and never sets. It simply hangs there, fixed at the same point in the sky, day after day, year after year, for as long as the planet has circled, and for as long as it will go on circling. The star is dim, the color of a dying coal, and it fills only a small portion of the sky above the horizon where it rests. Around it, the stars of the background galaxy are always visible, because the sky on this side of the world is never quite dark enough to hide them and never quite bright enough to wash them out. The planet keeps one face turned toward the heat, always, and one face turned away into a cold that has never once been broken by a single photon of direct starlight. This is what it means to be tidally locked. The same gravitational force that pulls the tides of Earth's oceans twice each day has, over billions of years, slowed the rotation of this smaller world until it stopped, until the planet's spin and its orbit matched perfectly, until one side and one star became permanently, inseparably paired. It is a slow process. It is patient the way only gravity can be patient, working across millions of years in increments too small to measure in a single lifetime. Red dwarf stars are the most common stars in the galaxy. 3 out of every 4 stars belong to this class. They are small, cool, and faint, burning so slowly and so carefully that the oldest of them have been burning since nearly the beginning of the universe, and will go on burning for trillions of years more. A red dwarf lives so long that the universe itself has not yet been around long enough to watch one die. And because they are faint, the region around each of them, where temperatures are warm enough for liquid water, is pressed in very close to the stellar surface, closer, in most cases, than the planet Mercury orbits our own sun. Any planet warm enough to hold an ocean around a red dwarf will almost certainly have been slowed to that locked, motionless rotation by the time it has aged enough to matter. The face of such a planet turned toward the star is warm. In the simplest models, it is perhaps too warm near the center of the sunward hemisphere, where the star's light falls almost directly overhead, baking the rock and boiling any surface water away. Out toward the edges of that lit face, where the starlight falls at a shallower angle, temperatures moderate, and then there is the terminator, the long line running from pole to pole, where day gives way to permanent night. Along that line, and not far to either side of it, temperature and chemistry meet in ways that might, under the right conditions, allow liquid water to persist. It is a narrow corridor of intermediate warmth, and it runs the full circumference of the world like a seam. On the night side, the cold is profound, without any direct starlight ever reaching it, without any summer or winter to provide relief. The dark hemisphere of a tidally locked planet grows cold enough to freeze the atmosphere itself. Nitrogen condenses, carbon dioxide solidifies against the rock. Whole layers of the air fall out of the sky and lie still on the ground, frozen solid, until nothing breathes them. This is the collapse that planetary scientists most fear for tidally locked worlds, the freezing down of the atmosphere on the cold side until the planet loses the gaseous envelope it needs to move heat from the warm side to the cold, until the atmospheric blanket that keeps any of the surface warm enough for liquid water simply disappears, drawn down into the ice on the hemisphere that never sees light. Whether this actually happens depends on the atmosphere's density. A thick, massive atmosphere carries more heat. It takes longer to cool. The winds that circulate from the warm side to the cold side blow with more force, carrying warmth around the terminator and across the dark face before that warmth can radiate away. Atmospheric circulation models, run over the past 2 decades on computer systems powerful enough to simulate global weather patterns, suggest that some atmospheres dense enough, composed of the right gases, can transport enough heat to prevent collapse. The dark side remains cold. It remains dark, but the air above it does not fall. And somewhere along the terminator, where the winds from the warm side arrive, still carrying their heat, liquid water might persist in rivers, or in lakes, or in shallow seas, tucked into the geography of the boundary. It is not the kind of habitability that Earth offers. Earth is bathed in light from all sides over the course of each rotation, its seasons distributed across the full surface, its oceans globally connected. A tidally locked world is asymmetric in a way that shapes everything: the circulation of its atmosphere, the distribution of its water, the chemistry of its rocks. If life exists on such a world, it would exist in a permanent geographical circumstance, unlike anything Earth's evolution has produced. Whether that matters, whether life needs a rotating world, a changing sky, the rhythm of seasons, is something no one yet knows. What researchers do know is that the red dwarf flares. A stellar flare is a sudden, intense release of energy from the star's surface, driven by the explosive reconnection of magnetic field lines that have wound and tangled in the stellar atmosphere. On the Sun, flares occur and send bursts of radiation outward into the solar system, but the Sun is large and the Earth is far enough away that most of the energy is diluted before it arrives. The flares of red dwarfs are a different matter. These stars flare frequently, and they flare intensely relative to their ordinary output. A planet orbiting a red dwarf in its habitable zone is so close to the star that when a flare erupts, the planet is bathed in ultraviolet and X-ray radiation at levels hundreds of times greater than any ordinary solar exposure on Earth's surface. Ultraviolet radiation at those intensities can destroy the molecules that make up the upper layers of a planet's atmosphere. It can strip gases away over time, accelerating the natural process by which the solar wind erodes an atmosphere from the outside. Planets without magnetic fields, which shield atmospheres from the charged particles that stream outward from a star, would be especially vulnerable. Proxima Centauri, the closest star to our own Sun, a red dwarf at a distance of just over 4 light-years, produces flares regularly and with intensity. The planet that orbits it, within what calculations suggest is the appropriate distance for liquid water, faces this radiation environment every time the star's magnetic field lines snap and reconnect. There is, though, another side to consider. Ultraviolet radiation at the right intensities and at the right wavelengths can drive chemical reactions that simple infrared warmth cannot. Some of the chemistry thought to be relevant to the earliest stages of life on Earth, the building of complex organic molecules from simpler components, may be accelerated by ultraviolet light. Some researchers have proposed that the frequent, intense flares of red dwarf stars might occasionally serve as triggers for prebiotic chemistry, delivering concentrated bursts of photochemical energy to a planet's surface or atmosphere. The evidence for this remains theoretical. No one has watched it happen, but the question of whether flares are purely destructive or whether they might also be occasionally generative is one that the field is actively working through without a settled answer. A red dwarf's light is also different in its composition. The sun produces light across a broad spectrum, including the visible wavelengths that Earth's plants have evolved to capture with chlorophyll. A red dwarf's light is heavily weighted toward the infrared, longer wavelengths, carrying energy in a form that green chlorophyll does not absorb efficiently. Photosynthetic organisms on a planet around a red dwarf, if they exist, and if they use something like photosynthesis, would need pigments tuned to different wavelengths. Some researchers have speculated about what colors those organisms might be, perhaps black, absorbing across the full spectrum, or deep red, tuned to the infrared that the star produces in abundance. These are speculations grounded in plausible chemistry, but they remain speculations. Stars of a different character, the G-type stars, the ones most like the Sun, have become the benchmark against which everything else in habitability science is measured. A G-type star burns steadily and reliably. It does not flare with the frequency or intensity of a red dwarf. Its light is distributed across visible wavelengths in a way that, on at least one world, produced photosynthetic life, complex chemistry, and an oxygenated atmosphere. It is comfortable and familiar in the way that familiar things become invisible. G-type stars represent only about 7 in every 100 stars in the galaxy, a fraction of the red dwarf's abundance, but they are the stars that anchor the imagination when the word star is said aloud. The Sun itself is a G-type star, and it has offered the clearest long-term record of what a G-type star does to the habitable zone over time. 4.5 billion years ago, when the solar system was young and the Earth was newly formed, the Sun was approximately 30% dimmer than it is today. This is not an approximation or a rough estimate. It follows from well-established stellar physics, from the way that hydrogen burning in a star's core gradually alters the core's composition and density, causing the outer layers to expand slightly and the total luminosity to increase. Stars brighten as they age on the main sequence. It is slow, and it is steady, and it has been happening since the first nuclear reactions ignited in the Sun's core. A 30% dimmer Sun means that the early Earth received substantially less energy than it does today. By the simple calculations of stellar flux and surface temperature, the early Earth should have been frozen. Glaciers should have covered the entire surface. The oceans, if they existed at all, should have been locked under ice kilometers thick. Yet the geological record is clear. Liquid water flowed on the early Earth. Rivers cut valleys. Oceans circulated. Life arose, or had already arisen, and was thriving in those ancient seas. The planet was not frozen. Something kept it warm. This puzzle has a name, the faint young sun paradox, and it has been actively discussed since Carl Sagan and George Mullen first described it clearly in 1972. The leading candidates for the warming agent are greenhouse gases. A young Earth with a thick atmosphere of carbon dioxide and methane could have compensated for the reduced solar input, trapping enough heat to keep liquid water stable. As the sun brightened over billions of years, the carbon cycle gradually drew carbon dioxide out of the atmosphere, reducing the greenhouse effect in rough step with the increasing solar luminosity. This elegant balancing act, more sunlight requiring less greenhouse gas to maintain temperatures, is one reason the carbonate silicate cycle is considered so important to the long-term stability of planetary climates. It is a slow geological thermostat, and it has been operating on Earth for most of the planet's history. The faint young sun paradox is a reminder that the habitable zone is not a fixed address. It moves. As a star brightens, the inner edge of the habitable zone pushes outward, and the outer edge pushes outward with it. A planet that was comfortably within the zone at the star's birth may find itself, billions of years later, closer to the inner edge or beyond it. A planet that was once too cold may warm into habitability as the zone drifts outward to encompass it. The habitable zone is better understood as a moving corridor than as a permanent ring, and a planet's long-term fate depends not just on where it begins, but on how its atmosphere and geology respond to the slow brightening that every main sequence star undergoes. Among all the different types of stars, the sun sits in a kind of middle ground, not the most common, not the longest lived, not the most luminous, but stable and steady over time scales long enough for complex life to have arisen and diversified on at least one world. The question of whether that stability matters, whether the particular character of the sun's radiation, its modest flare rate, its slow and predictable brightening, was necessary for life to develop on Earth, is one that cannot yet be answered. Earth is the only inhabited planet known, and the conditions that produced Earth's life cannot be separated from the conditions that were simply present. The specific may be necessary, or it may merely be what happened. Binary star systems present a different kind of complexity. About half of all sun-like stars in the galaxy exist not alone, but paired, two stars orbiting each other, their combined gravitational field shaping everything around them. A planet in such a system can orbit in one of two configurations. It can orbit closely around just one of the two stars, staying near enough to that star to remain in its gravitational dominance, while the companion star circles far away. Or it can orbit both stars from a wide outer distance, looping around the entire binary pair in a path that keeps it far enough from both to remain stable. The first kind of orbit is called an S-type orbit, the S standing loosely for the orbit around a single star. The second kind is called a P-type orbit for the planet circling the pair. In a binary system, a planet's received starlight fluctuates in ways that don't occur around a single star. As the two stars orbit each other, their combined output as seen from the planet changes. Closer together, they may add their light. Farther apart, the geometry distributes it differently. Seasons in a binary system are not simply the result of axial tilt, as on Earth. They are compounded by the orbital mechanics of the two stars, producing a complex rhythm of warmth and cooling that has no simple equivalent in a solar system with a single sun. Whether planets in binary systems can maintain the long-term climate stability that life seems to require, based on everything the field has inferred from Earth, is a question the models have been refining for decades. A planet called Kepler-16b, confirmed in 2011 from data collected by the Kepler Space Telescope, demonstrated that P-type orbits around a binary pair are not only theoretically possible, but actually exist. The planet orbits two stars, one slightly smaller than the Sun, one significantly smaller, on a stable path that takes it around both of them on a period of about 229 days. From the planet's surface, if it had a surface of the kind one could stand on, Both stars would be visible together in the sky, sometimes close, sometimes separated, the light arriving from two sources that cast two shadows and set in sequence or together, depending on where in the orbit the planet currently sits. Kepler 16b is a cold, gaseous world, not a promising candidate for life in any straightforward sense. But its existence settled a prior question. A planet could find a stable orbit around a binary system. The gravitational dance that seemed like it might fling any planet loose had not, in this case, done so. The conditions that produce stable planetary orbits in binary systems depend on the separation between the two stars, the ratio of their masses, and the orbital inclination of the planet relative to the stellar pair. Too close together, and the two gravitational fields create regions of complex instability. Too far apart, and an outer P-type orbit might be stable but too cold, while an S-type orbit close to one star might be pulled out of its path by the gravitational perturbation of the distant companion. Between these extremes lie configurations that allow stable, habitable zone orbits to persist across geological time. They are not rare in principle. The modeling suggests that stable zones exist in many binary configurations, but finding them observationally has required the kind of precision photometry that only space-based telescopes have been able to provide. The full range of stellar diversity, from the most common red dwarfs to the stable G-type stars to the brighter, hotter F-type stars, from solitary suns to binary pairs, means that the habitable zone concept applies not to one configuration, but to dozens. Each stellar type produces a habitable zone at a different distance, with a different width, illuminated by light of a different spectral character, and each zone persists for a different duration. A massive hot star burns through its hydrogen fuel rapidly, remaining on the main sequence for only a few 100 million years before swelling and dying, perhaps not long enough for complex life to develop, if the timescales observed on Earth are any guide. A red dwarf, burning slowly and carefully, will remain in its current state for far longer than the current age of the universe. The question of duration leads to a more demanding habitability criterion than the simple instantaneous habitable zone. Any moment snapshot of a star and its planets will show which planets currently receive the right amount of flux for liquid water. But life, at least as it is understood from Earth's example, requires not just a moment's warmth, but a sustained geological era of stable conditions, billions of years, during which chemistry can become biology, single cells can become complex organisms, and complex organisms can develop the kind of internal complexity that allows them to survive a changing environment. A planet that is in the habitable zone now, but was outside it for the first 2 billion years of its existence, or will be outside it in another billion years, faces a different history than one that has been continuously warmed to liquid water temperatures across its entire life. This longer view produces a more stringent concept. Within the broad ring of the instantaneous habitable zone, the region where a planet could, in principle, support liquid water right now, sits a narrower band that has remained within the habitable zone for the full duration of the star's main sequence life. This narrower band is called the continuously habitable zone, and it accounts for the gradual outward drift of the habitable zone as the star brightens over time. A planet at the inner edge of the instantaneous zone may have been too warm in the star's youth. A planet at the outer edge may have been too cold early on and will be too warm in the star's old age. The continuously habitable zone excludes those transient cases, keeping only the planets that have held their place in the warmth across the full sweep of their star's productive life. The continuously habitable zone is narrower, and the list of worlds that satisfy it is shorter. Around a G-type star like the Sun, the continuously habitable zone over the full 5 billion year main sequence lifespan is a thinner ring than the instantaneous zone. Earth currently sits within it, but only because Earth's geological and atmospheric systems have actively compensated for the Sun's brightening. The carbonate-silicate cycle drawing down carbon dioxide as solar flux increased, keeping surface temperatures within the range where liquid water persists. A planet without that mechanism, without volcanic resupply of carbon, and without silicate weathering to remove it from the atmosphere at the right rate, might have difficulty maintaining the compensation across billions of years. The time dimension of habitability is easy to overlook when the habitable zone is discussed as a simple ring around a star. It looks in the common diagram like a fixed object, a circle at a defined distance, shaded to indicate warmth. But the diagram is a snapshot, and the snapshot is misleading. The zone has always been moving, is moving now, will continue to move as long as the star burns. The Earth that sits comfortably in today's habitable zone is a planet that has tracked a moving target for 4.5 billion years, not through any foresight or intention, but because the geological processes that were already operating happened to produce feedbacks that kept pace with the slowly increasing solar output. That coincidence, if it is a coincidence, is not something that every planet in every system can be assumed to replicate. Somewhere in the galaxy, around one of the 100 billion stars that populate the Milky Way's disk, there is almost certainly a planet that has held its place in the continuously habitable zone of a steady star for long enough to allow whatever chemistry and biology and geological cycling can produce when given sufficient time, perhaps more than one, perhaps many. The continuously habitable zone does not make habitability rare. It makes habitability's requirements clearer, and clearer requirements are more useful than vague ones. The light from a red dwarf reaches its tidally locked companion world and falls only on the same half, always. The sun's light falls on Earth from a slightly different angle each day, each year, across billions of years of steadily increasing intensity. Two stars in a binary pair share their light with a distant planet that feels their combined warmth shift over decades and centuries as they circle each other. In each case, the central question is the same, and it is the same question Huang Su was asking in 1959 when he first tried to define the zone formally. Is there enough warmth, in the right form, sustained for long enough to keep water liquid on a rocky surface? The question has grown more detailed since then. The zone has grown more complex. The stellar types it must account for have multiplied as the observed diversity of stars has come into clearer focus. What has not changed is the underlying physics. Starlight spreads outward in all directions from its source, growing fainter with the square of the distance. A planet intercepts a portion of that light, proportional to its cross-section and its distance. The light heats the surface, and the surface radiates that heat back into space. The balance between incoming light and outgoing radiation determines the temperature. An atmosphere, if one exists, alters that balance through the greenhouse effect, trapping some of the outgoing radiation and warming the surface further. The carbonate-silicate cycle, if it operates, adjusts the atmospheric composition in response to temperature changes, providing a slow geological regulation. These processes apply around every star, in every system, regardless of the stellar type. What changes is the magnitude and the wavelength of the incoming light, the distance at which the balance falls, and the duration over which the balance must hold. The red dwarf that holds one face of its companion planet in permanent amber glow is obeying the same physics as the sun. The binary pair whose combined light floods a distant orbiting world follows the same inverse square law as every isolated star. The G-type star that has warmed its planetary system steadily for 5 billion years and will warm it for 5 billion more is not doing anything different from the red dwarf burning slowly in its corner of the galaxy, only at a different rate, on a different schedule, from a different distance. The physics is the same, the particulars are not. There is something settled about that. The universe applies its rules without exception. The same forces that shaped this solar system shaped every other one. And somewhere in the enormous ancient diversity of stars and the worlds that circle them, those rules have had billions of years and countless configurations in which to work. The continuously habitable zone is not a guarantee. It is a place where the conditions have been right for long enough that what can happen, given time, has had time to begin. The star that never moves in the sky of its locked companion world has been burning for longer than the sun has existed. Its planet has been turning the same face toward the same point in the sky for most of that time, the winds moving in long, slow currents from the warm hemisphere to the cold, carrying heat that dissipates slowly into the permanent night. Whether water pools anywhere in that system, along the terminator, in the atmosphere, beneath the surface, no one knows yet. But the physics that would allow it is the same physics that allowed an ocean to persist on Earth, and the time that has been available to that system is longer than the time that has passed since the first cell divided in Earth's ancient sea. Deep time has a weight that numbers cannot fully carry. 4 billion years is a span in which a species can arise and cover a world, and look up at the stars and begin to ask where else something like them might be. 10 trillion years is a span the universe has not yet measured out in the life of any star. The red dwarfs will still be burning when all the G-type stars have spent their hydrogen and cooled into embers. If life requires only time and liquid water and the slow work of chemistry, the red dwarfs have more time than any other stellar class, more time than can easily be imagined, more time than the universe has yet used. And if the tidally locked worlds around them are not quite like Earth, not rotating, not evenly lit, not seasonally variable in the way that Earth's axial tilt produces, they are still governed by the same thermodynamic patience that has governed every habitable place. The heat comes in, the heat goes out. In the narrow space between those two flows, at the right distance from the right kind of star, under the right thickness of atmosphere, liquid water can rest in the low places of the rock and wait. The star hangs unmoving in the sky above the terminator. The wind from the warm side arrives with its cargo of heat, slow and steady and ancient. Whatever lives or has ever lived, or will one day live along that seam of borderline warmth, does not know that a star of a different color, at a different distance, has been carefully catalogued and measured and placed within a zone boundary calculated by researchers working from spectroscopic absorption data gathered across decades of careful observation. It knows only the temperature of the rock and the moisture in the air and the long uninterrupted continuity of the star that does not rise or set. It exists within the patience of the physics, the same physics that has always governed every warm and watered place in the universe, working slowly and without witness across the full deep measure of available time. A small dark circle appears against a bright star. It moves slowly. It takes hours to cross the full width of the stellar disk, drifting from one edge to the other in a motion so gradual it seems, at any given moment, to be standing still. But the instruments are patient. They record every fraction of a percent of dimming as the planet steps in front of its star, and from that dimming, from the precise depth and duration of shadow, scientists can calculate the size of the world, the length of its year, the distance it travels. This is how Kepler 452b was found, not through a telescope aimed at something visible, but through the shadow a world leaves on its own star as it passes by. The planet is about 60% wider than Earth. Its year lasts 385 days. Its orbit is close to circular, tracing a path that keeps it at a nearly steady distance from its host star, a distance that places it by every boundary calculation available within the habitable zone. Around a G-type star, a star like the Sun, but older, 1.5 billion years older, a star that has had that much longer to brighten. Slowly, as the hydrogen at its core burns down and the energy output climbs, degree by degree, across the eons. What that age difference means for Kepler 452b is something researchers still hold carefully as a question more than an answer. If the planet's story resembles anything like the inner solar system's history, the star's increasing brightness may already be pressing hard on whatever climate machinery the world once had. The inner edge of warmth is moving outward, as it always does around aging stars, and the planet, fixed in its orbit, cannot follow it. That single transit signal, that dip in brightness, lasting just hours, opened a question that the numbers alone cannot close. A world the right distance from the right kind of star, and still, only the beginning of a longer list. The stars themselves carry their habitable zones like slow rings of warmth spreading outward into cold space. Every star has one. The distance and width of the ring depend on how bright the star is, how hot, how stable across time. And the planets caught within those rings are the ones the search has always been directed toward. Rocky worlds in the right place, at the right moment in their star's long life, holding the particular distance from stellar fire that allows, in principle, for liquid water to exist on open ground. In the search that followed the first confirmed detections of planets around other stars, patience became the instrument as much as the telescopes themselves. Thousands of candidate worlds collected in the data. Most were gas giants, or worlds too close or too far, too large or too small. A smaller number sat inside their star's habitable zone. A smaller number still were rocky and Earth-sized. And within that already narrow group, a handful became subjects of serious, careful, sustained attention. Proxima Centauri hangs 4.25 light-years from the Sun. It is the nearest star to the solar system, a red dwarf, small and dim, burning cool at the bottom of the stellar mass range. Its light is faint enough that seen from Earth it is invisible to the eye, but it has a planet. The minimum mass of that planet is just above Earth's. Its orbit takes 11.5 days to complete, circling so close to its star that the star fills a large portion of its sky, far larger than the Sun fills ours. At that distance, around a star that dim, the planet sits within the habitable zone. The received energy is comparable to what Earth receives from the Sun. On paper, the temperature budget works out, but the star is a red dwarf, and red dwarfs are not quiet suns. Proxima Centauri flares. It erupts with sudden bursts of ultraviolet and X-ray radiation that dwarf anything the Sun regularly produces. Waves of high-energy light that wash over the nearby planet in pulses that repeat across days and weeks. Whether a planet as close as Proxima Centauri b can hold an atmosphere against that steady, energetic pressure is a question the current data cannot fully settle. Hydrogen and helium, being light, escape most easily. Heavier molecules can persist longer, but only if something generates them fast enough to replace what is lost. Only if the planet began with enough volatile material. Only if the star's earliest, most violent phase, when flares came more frequently and more intensely, did not strip the atmosphere entirely before the planet had a chance to stabilize. The light from Proxima Centauri has not yet told its own story clearly enough. The planet has not yet been observed in transit, which would allow its atmosphere, if one exists, to be probed for chemical signatures. What exists is the gravitational signal, a small periodic tug on the star, detectable in the shifting of spectral lines, a wobble translated into mass and orbit. The world is real. What it holds is still open, 39 light years away, in a direction corresponding to the constellation Aquarius. A small cool star pulls a different kind of attention. The star is classified as an ultra-cool red dwarf, its surface temperature well below the sun's, its luminosity a fraction of a percent of the sun's output. It is barely large enough to sustain fusion. Around it, 7 rocky planets orbit in a tight-nested arrangement, their periods ranging from just over a day to nearly 20 days. All 7 are roughly Earth-sized. This is the TRAPPIST-1 system. The 7 planets orbit so close together and in orbits so compact that the entire arrangement would fit within the distance Mercury travels from the Sun. If the outermost of the 7 were placed in our solar system, it would still be deep inside the orbit of Venus. And yet, 3 of these worlds, the 5th, 6th, and 7th, counting outward from the star, lie within the boundaries of the habitable zone, as calculated for this star's luminosity. TRAPPIST-1e is the one researchers return to most often when naming the system's best candidate. Its orbit gives it a stellar flux close to what Earth receives from the Sun. Its size and mass, inferred from gravitational interactions with its neighboring planets, are consistent with a rocky composition. The star it orbits is dim enough that the habitable zone sits close, but the planet sits within it. The conditions, on paper, permit liquid water. Paper conditions and surface conditions are not the same thing. The star is an M-dwarf, and M-dwarfs flare. The planets are almost certainly tidally locked, one face permanently toward the star, one face permanently turned away into cold darkness, the terminator line between them a perpetual boundary between heat and ice. Whether any of these 7 worlds holds an atmosphere thick enough to redistribute heat, to carry warmth from the illuminated hemisphere around to the dark side, is a calculation that depends on geology, on volcanic history, on the original composition of the planet, on the strength of any magnetic field that might deflect stellar wind. The transit method that first revealed this system's architecture also allows, in principle, for atmospheric study. When a planet passes in front of its star, a small fraction of starlight filters through the edges of the planet's atmosphere, if one exists, and the chemical fingerprints of that atmosphere, the wavelengths absorbed by particular molecules, can in principle be read from the light that arrives at a telescope. This is difficult. With the TRAPPIST-1 planets, which are small and orbit a dim star, it requires the sensitivity of the largest instruments yet built. The James Webb Space Telescope has begun this work. Early results have come back for some of the inner planets, and for those, the data suggests thin or absent atmospheres, at least at the surface. The outer planets, including 1e, remain less clearly characterized. The investigation is ongoing, careful, and slow. The TRAPPIST-1 system matters for a reason beyond its individual planets. It demonstrates that compact, rocky, multi-planet systems around small, cool stars are possible. It demonstrates that planets within habitable zones can orbit in stable resonance with each other across geological time. It demonstrates that one red dwarf, The most common kind of star in the galaxy can host not one, but several rocky worlds in the zone at once. If these configurations are common, and the evidence suggests they may be, then the number of potentially habitable worlds in the galaxy is very large. But the solar system itself contains its own inhabited worlds and its own cautionary cases, and they are close enough to study directly and in depth, which no exoplanet yet is. Venus lies inward from Earth, slightly smaller, similar in bulk composition, formed under roughly comparable conditions in the early solar system. Its surface is dry. Its atmosphere is 90 times denser than Earth's at sea level, composed almost entirely of carbon dioxide, pressing down with a weight felt in the bones of any imagined visitor. Surface temperatures reach nearly 900 degrees Fahrenheit. The planet radiates heat in all directions, a world locked inside its own thermal prison. This was not always the case. The best current picture of Venus's early history, built from geochemical models and surface isotope ratios, suggests the planet may have hosted liquid water oceans for billions of years. Some models place that window of habitability as recently as 700 million years ago. The planet may have sat for much of its early history at the warm inner edge of what the habitable zone calculations describe. And then something changed. The exact trigger is still debated, whether a massive volcanic event overwhelmed the climate system, whether the slow brightening of the sun pushed water vapor into the upper atmosphere faster than it could return to the surface, whether internal cooling eliminated the magnetic field before the atmosphere had developed the chemistry to protect itself. What is not debated is what happened next. Water vapor rose into the upper atmosphere, where ultraviolet radiation broke the molecules apart, and the hydrogen component, being light, escaped to space. The oxygen reacted and was lost. The ocean, molecule by molecule, was carried away. Carbon dioxide, outgassed from volcanic activity, accumulated without liquid water to dissolve it back into rock. The greenhouse grew thicker. The temperature rose. The planet arrived at its current state, a world that sits in astronomical terms just inside or just at the inner boundary of where the habitable zone begins, but whose surface has long since become something entirely other than habitable. Venus is a lesson written in planetary history. Being in the zone did not save it. The zone marks where liquid water is possible. Venus demonstrates that possibility and actuality are not the same thing, and that a world's own internal processes, its volcanism, its atmospheric chemistry, its history of water loss, can remove it from habitability even while it remains in the right region of space. Mars, on the other hand, sits close to the outer edge. Its orbit takes it far enough from the sun that temperatures fall well below freezing at the surface for most of the year, and its thin atmosphere, less than 1% the density of Earth's, cannot hold enough pressure for liquid water to persist in the open. Water placed on the Martian surface today would either freeze or boil away, depending on elevation and time of day, without ever holding still as a liquid. The surface, however, carries a different history. Valley networks cut across ancient highlands, carved by water that flowed over geological time. River deltas fan out into basins that were once shallow lakes. Minerals form only in liquid water crystallized in layers across hundreds of kilometers of terrain, preserved in sedimentary rock that Martian rovers have examined directly. Mars was wet. Mars was warm enough, under a different sky, to hold rivers and lakes, perhaps for hundreds of millions of years during the first billion years of solar system history, long before Earth's first complex life. Something took that away. The current understanding points to the loss of Mars's magnetic field, perhaps 3 to 4 billion years ago, as the hinge on which its fate turned. Without a magnetic field, the planet's atmosphere was exposed to the solar wind, a continuous stream of charged particles flowing outward from the sun, and over geological time, that wind stripped away the atmosphere, layer by layer, molecule by molecule. As the atmospheric pressure dropped, liquid water could no longer persist. As the pressure fell further, the greenhouse effect weakened. As the greenhouse weakened, the surface cooled. The water that remained retreated underground into the poles, where it persists today as ice. Mars sits near the outer edge of the habitable zone. Like Venus at the inner edge, it shows that position alone is not enough. Geophysics matters. Internal heat matters. Magnetic protection matters. The zone is the starting point. It identifies where to look, where the fundamental temperature budget makes liquid water plausible. What actually determines whether a world is habitable is a longer, more complex story. Rocky planets carry their habitability in their mass as much as their orbit. A world needs to be massive enough to hold an atmosphere over geological time, because lighter gases escape from lower gravity worlds more easily, and because atmospheric mass determines whether surface pressure can remain high enough for liquid water to exist. Below roughly a third of Earth's mass, the evidence suggests a planet struggles to maintain the kind of thick atmosphere that buffers surface conditions across billions of years. But mass also has an upper limit on habitability, and that limit arrives in a different way. A planet significantly more massive than Earth, several times more massive, may retain such a large inventory of water from its formation that the surface becomes completely covered. There is no exposed rock, there is no continent. Volcanic gases that would normally reach the atmosphere are dissolved back into the ocean before they can cycle through the carbon and silicate chemistry that on Earth acts as a long-term thermostat, drawing carbon dioxide out of the air when temperatures rise and releasing it when they fall. On a world entirely covered by water, that thermostat does not function. The planet may sit at the right distance from its star. It may have liquid water, but the stability mechanism that allows Earth to stay within a habitable range across billions of years, the slow geological cycle that buffers the climate, may be absent. Such a world could still, in principle, host life, but the kind of long-term stability that allowed complex life on Earth to develop across billions of years requires a different planetary architecture than a world submerged entirely in its own ocean. These are not hypothetical extremes. Planet formation models, combined with the compositional data arriving from transit observations, suggest that water worlds, planets with water comprising a significant fraction of total mass rather than the thin surface layer it represents on Earth, may be common around smaller stars. Whether life could develop and persist on such worlds is a question that cannot yet be answered, and the answer may depend on what kind of life is considered and on what timescale. Kepler 452, boarding its aging star, carries all of these considerations at once. It is in the zone. Its star is sun-like, stable across long periods, producing the kind of steady radiation that allows chemistry to proceed without constant disruption. Its size suggests it may be rocky, though with only size and orbital information available, the composition can only be estimated, not confirmed. It is possible the planet is a scaled-up rocky world with a thick atmosphere. It is possible it has already lost surface water under the increasing luminosity of its host star, as the star has brightened over the past 4 billion years, and the habitable zone has shifted slightly outward, away from the planet's fixed orbit. The planet cannot tell us yet. It has not transited its star in a geometry that allows its atmosphere to be probed. It remains, for now, a large shape detected in shadow, a number in a catalog, a subject of careful extrapolation rather than direct measurement. What the discovery of Kepler 452b represented, what it still represents, is something more structural than any individual set of measurements. It showed that Earth-sized planets in near-Earth orbits around Sun-like stars exist. They are not theoretical. They are not statistical artifacts. They are real worlds, circling real stars, following real orbits. The habitable zone is a real location in space, and real planets sit inside it. The calculations that define the zone's edges were not built to be perfect. They were built to be useful. The inner boundary, where runaway evaporation begins, and the outer boundary, where carbon dioxide condenses and ceases to warm, are derived from climate models that use simplified planetary atmospheres that assume certain compositions and pressures and reflectivities that cannot yet account for cloud cover in precise detail or for the specific photochemical interactions that a different kind of atmosphere might produce. The boundaries are estimates of where habitability becomes unlikely given our best current models. They are not walls. This is the honest position the science occupies. The habitable zone identifies the region around a star where liquid water is plausible at the surface of a rocky planet with an Earth-like atmosphere. It is a first filter, the first and most important question asked when a new planet is discovered. Everything afterward is refinement. An enormous planet sitting at the right orbital distance may be a gas giant with no solid surface. A rocky planet at the right distance may have lost its atmosphere to stellar activity. A rocky planet with an atmosphere at the right distance may have a chemistry that makes its surface uninhabitable regardless of temperature. A world may be in the zone and cold because it is too small. It may be in the zone and hot because it is too large. It may be in the zone and covered entirely in water, or entirely in rock, or tidally locked with one side frozen and one side burning. The zone tells us where to begin. The planets themselves tell us what is actually there, one measurement at a time across years and decades of careful observation. The solar system provided the framework for all of this. Earth sits inside the zone, and Earth is habitable not just by the technical definition of liquid water, but abundantly, extravagantly, deeply habitable, covered in oceans, layered in biology from the deep crust to the upper atmosphere, cycling water and carbon and nitrogen through continuous planetary systems that have kept conditions within a livable range for billions of years. Mars and Venus bracket the zone on either side and demonstrate how neighboring worlds can fail, each in its own way, to maintain what Earth has held. That bracket, Venus, Earth, Mars, gave the first habitable zone estimates their empirical grounding. If Venus was once habitable and Mars was once habitable, the zone must extend at least as far inward as Venus and at least as far outward as Mars. These are the optimistic limits. The conservative limits, derived from climate modeling rather than solar system history, sit somewhat narrower, and Earth sits comfortably within both. The difference between the conservative and optimistic zones approximately doubles the number of planets classified as potentially habitable when applied across the known exoplanet catalog. How those lines are drawn matters practically for the question of how many worlds are worth investigating with limited telescope time. The transit of Kepler 452b, that small dark circle crossing slowly in front of its star, is still the cleanest image for what the habitable zone concept was built to produce. A star, a planet, a shadow. The shadow tells us the planet exists, tells us its size, tells us its year. And from the year, from the orbital distance it implies, from the luminosity of the star, comes the number that places the planet within the zone or outside it. The calculation is simple. What it means is not. Being in the zone is one fact about a world. It is the first fact. It is the fact that makes a planet worth asking further questions about. It does not answer those questions. It does not confirm an ocean or an atmosphere or a rain that falls and collects in basins, or the chemistry needed to assemble the first self-replicating molecule. It says only that here, at this distance, around this star, the energy arriving at the surface falls within the range where water can be liquid. The rest of the answer requires the planet itself. The 7 TRAPPIST-1 worlds are close enough and bright enough in transit that the rest of the answer is being slowly assembled. The instruments exist now to begin reading their atmospheres, to look for water vapor or carbon dioxide or methane in the filtered starlight. The process is slow. Each transit lasts a few minutes. Each transit yields a tiny fraction of signal. Dozens of transits, accumulated over months of observation, begin to build a picture. The picture, so far, is incomplete, but it is growing. Proxima Centauri b has not yet transited. Its shadow, if it falls across its star at all, has not yet been caught at the right angle. The planet remains known only through the pull it exerts. A slight, measured, repeated tug, detectable in the color of starlight, as the star moves toward and away from Earth in response to the orbit of its companion, mass and period, distance and zone, and beyond that, for now, uncertainty, sitting quietly like a door that has not yet been opened. The ancient surface of Mars, reconstructed from the chemical and geological record left in the rock, is an image of what the zone once permitted and then could not sustain. River valleys that have not carried water for 3 billion years. Lake sediments that formed when the atmosphere was thick enough to hold rain. Minerals that crystallized slowly in standing water at the bottom of crater lakes. The record is clear. Mars was a different world once, and the zone was not wrong about it. The zone said the energy budget permitted liquid water, and liquid water was there. What the zone did not, could not predict was what the planet itself would do with its magnetic field, its volcanism, its internal heat. That is the limit that the concept carries openly and honestly. It was always designed to be a first filter, not a final answer. Huang Sushu, who first drew the boundary formally in 1959, was describing where to look, not what would be found there. The models that followed, refining the edges, adjusting for albedo and atmospheric chemistry, incorporating the spectroscopic behavior of different greenhouse gases, were all attempting to make the filter more precise, not to pretend that passing through the filter was equivalent to being habitable. The habitable zone is a question the sky asks of itself. For every star, at every distance, it asks, could water be liquid here? And for those distances where the answer is yes, the question becomes more specific, more demanding, more dependent on details that only the planet can provide. Mass, composition, atmosphere, magnetic field, geological activity, orbital stability, stellar behavior across geological time. Each new question is harder than the one before it. Each new measurement answers one part and opens another. The small dark circle moves slowly across its bright star. The instruments record the dimming. The calculations proceed. A world is confirmed. A year is measured. A distance is inferred. And from that distance, from the luminosity of the star, a simple comparison is made, within the zone or outside it, and the planet joins a short list of places in the sky that the science considers worth continuing to ask about. That list is not long, Among the thousands of confirmed planets, the number of rocky worlds in habitable zones is small. Among those, the number with the right mass range and the right stellar host to make atmospheric characterization feasible is smaller still. Each one represents years of accumulated observation, careful instrument calibration, statistical analysis, and the patient accumulation of transits. Each one is a real world. The rocky planet at the right distance from a stable star, covered in liquid water, cycling carbon through its crust and atmosphere, accumulating biochemistry across billions of years. This is one possibility among many. Earth is the only confirmed example. Every other candidate is still a question in the data. The habitable zone marks where the questions are worth asking. The worlds themselves, each in their own slow time, hold the answers. The surface of a planet in the zone, at the right mass under a quiet star, can hold a still pool of water through the long balance of a geological afternoon. Not boiling, not frozen, catching light across its surface, reflecting it back into a sky thick enough to hold it down, losing it slowly to evaporation, replenishing it from rain. A pool that persists not for a day or a year, but for millions of years, while the rock beneath it weathers slowly, while the water carries minerals from high ground to low, while chemistry accumulates in the shallows. Whether that chemistry assembles into something that replicates itself, that organizes into cells, that over billions of years produces the kind of complexity that fills oceans and covers continents, that is a different question, a longer question, one that the habitable zone does not answer and was never meant to. The zone is the condition. What happens within the condition is still being learned, here on the one world where the full story is available to read. The pool persists, the water moves, the light falls across the surface in the steady ancient rhythm of a planet in its orbit, turning slowly, holding warmth from the star that drew the boundaries of where it could be. Somewhere out there, around one of the many stars in whose direction the telescopes have already turned, there is perhaps another pool, another surface, another balance between heat and cold, where water rests in the open and does not escape. The zone does not promise it. The zone only says that, in that direction, at that distance, the energy is right. Everything else remains to be found. Europa hangs in the dark beyond the reach of the sun's warmth, a small white sphere crossed with reddish-brown lines that press up from beneath the ice like the seams in old cracked clay. From a distance it looks simple, a moon, a frozen thing. But those lines are pressure ridges, forced upward from below by something moving underneath the surface, something vast and dark and liquid, shifting with the slow pull of gravity from the planet it circles. The ice above it is perhaps 20 miles thick in places, and below that ice, in the complete absence of sunlight, an ocean of liquid water stretches away in every direction, as wide across as the moon itself, never having seen the light of anything. The ocean beneath Europa's ice does not need the sun. It has never had it. What keeps it liquid is not proximity to a warm star, but the constant squeezing and releasing of the moon's interior, as Jupiter's enormous gravity needs it from outside, and as the competing gravitational pulls of neighboring moons tug and release in their own steady rhythms. This process is called tidal heating. The rock beneath the ocean flexes, and in flexing it generates warmth, and that warmth rises through the floor of the sea in slow currents that keep the water from freezing through. In the cold outer reaches of the solar system, more than 5 times farther from the sun than the earth, an ocean persists, not despite the cold, but through a mechanism the cold cannot touch. The ice above is not featureless. where the pressure ridges meet and cross, where the crust has cracked and refrozen in long cycles spanning thousands of years. The surface carries a record of motion far below. Dark reddish material, minerals and salts carried upward through the ice from the water beneath, stains the pale surface in long streaks. Radiation from Jupiter's magnetic field strikes the surface continuously, breaking apart molecules and forming new compounds in the thin ice. The chemistry at Europa's surface is being constantly rearranged by energy that arrives not from a star, but from a planetary magnetic field, a process utterly unlike anything the original habitable zone concept was designed to account for. The concept was built around stars. It was built around a central source of light and heat, a planet at a careful distance, and the liquid water that could exist on a surface warmed by that light. It described a ring around a sun, the right distance, the right temperature, the right amount of flux arriving from above. It was an honest and useful framework built from the physics of starlight and the chemistry of water, and it brought the search for life from abstraction into something that could be mapped and measured and applied to real worlds. But Europa is not in any ring around the sun. Europa is in the cold, and the cold has not stopped it. Beneath the ice, the ocean is dark in a way that surface oceans are not. No photon from the sun reaches it. No season turns there. No tide responds to a passing moon, because Europa is itself the moon, and the ocean is inside it. The water is cold, but it is not frozen. It is old, in the way that enclosed things are old, circulating slowly, in contact with the rock below, carrying minerals dissolved from the seafloor in long, slow currents that rise and fall as the interior flexes and breathes. What lives in that water, if anything does, would have no reference point for day or night, for warmth from above, for the kind of biology that begins with sunlight falling on a leaf. It would live on chemistry alone. A spacecraft called Europa Clipper left Earth in the autumn of 2024, carrying instruments designed to probe the ice and the ocean beneath it from orbit. It will not land. It will pass close, again and again, measuring the thickness of the ice, the composition of the surface, the shape of the magnetic field, the gases escaping into the thin surrounding space. It will not answer the question of whether the ocean holds life, but it will answer many of the questions that come before that one: how deep the ocean is, how warm the floor might be, what chemistry the water carries, and those answers will narrow the distance between what is known and what remains open. The idea that life requires sunlight is not a scientific law, it is a habit of familiarity. Every living thing a person has ever seen, or touched, or eaten, or been, traces its energy ultimately back to sunlight, back to the green cells that captured it, to the photons that drove the chemistry that built the sugars that fed everything else. The assumption is so deeply embedded that it barely registers as an assumption, but it was never a law. It was always a description of how life happens here, on a surface warmed by a nearby star. Whether it is the only way was always a separate question. That question acquired a partial answer in the late 1970s when a submersible descended into the deep Pacific and found on the floor of the ocean a world that sunlight had never reached and yet was covered in life. The vents on the seafloor released hot mineral-rich water from below, and around those vents, dense communities of organisms, tube worms, clams, shrimp, crabs, microbes, lived and fed and reproduced in the total dark. The energy they ran on came not from the sun, but from chemical reactions between the hot vent fluid and the cold surrounding water. It was a discovery that changed not just what was known about the deep sea, but what was understood about the conditions life requires. Sunlight, it turned out, was one option. Chemistry was another. Saturn's moon Enceladus is smaller than Europa, small enough that it might seem an unlikely candidate for anything extraordinary. Its surface is nearly white, almost perfectly reflective, covered in clean, fresh ice that suggests the surface is geologically young, constantly renewed from below. At its south pole, in a region of long parallel fractures called tiger stripes, water erupts from the interior in tall plumes that rise above the surface and disperse into space. The plumes carry ice crystals, water vapor, and something more, organic molecules, silica particles, that form only in hydrothermal conditions, and molecular hydrogen, which is released when hot water reacts with certain minerals in the absence of oxygen. The spacecraft that discovered all of this flew directly through the plumes and sampled them on the way past. The deep ocean of Enceladus was reaching up through the ice and offering its contents to anyone passing close enough to catch them. What the sampling found was a complete set of chemical ingredients: water, carbon compounds, nitrogen, sulfur, and hydrogen, which in certain chemical environments becomes a source of energy, the same kind of energy that hydrothermal vents on the Earth's seafloor release to the communities gathered around them. The ocean of Enceladus, locked beneath ice at a distance from the sun where nothing should be liquid, appears to contain active hydrothermal chemistry on its floor: hot water meeting cold rock, minerals dissolving and reacting, hydrogen rising through the water column. And somewhere above the floor, the chemistry of those reactions mixing into an ocean that stays liquid, not because a star warms it, but because the moon's interior cannot stop flexing under the pull of Saturn's gravity. Later analysis of the Enceladus plume material found phosphorus-bearing compounds. Phosphorus is essential to the chemistry of life as it exists on Earth, present in the backbone of every strand of genetic material, in the molecules that carry energy inside every cell. When it was detected, the inventory was nearly complete. All 6 of the chemical elements considered most essential to life, as it is known: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, had been found in the plumes rising from the ice of a small moon in the outer solar system, not on a planet orbiting in a habitable zone around a star. In a plume of water from a subsurface ocean warmed by nothing more than gravity and rock. The original habitable zone concept had no category for Enceladus. The framework described a ring of space around a star, defined by the temperature at which water could exist as a liquid on a planetary surface. Enceladus is not in a ring, it is not on a surface. It is a moon of a gas giant, and its water is buried under miles of ice, and its energy source is gravitational tidal friction between rock layers deep in its interior. The framework was designed to answer one question: which planets around which stars might have liquid water on their surfaces. It was never designed to describe a small icy moon with an active hydrothermal ocean beneath its shell. That is not a criticism of the original framework. It was designed before Enceladus's ocean was known to exist. It is simply a description of the distance between a first approximation and the full landscape it was trying to map. Titan is stranger still. Saturn's largest moon has a thick orange atmosphere of nitrogen and methane, and beneath that haze on its surface, there are lakes and rivers and seas, not of water. The surface of Titan is cold enough, nearly 200 degrees below the freezing point of water, that water ice is hard as granite there, and the liquid that fills the low places in the landscape is methane and ethane, hydrocarbons that remain liquid in the cold, the way water remains liquid in warmth. The lakes near the North Pole are dark and still under the orange sky, and rivers of liquid methane have carved channels in the ice rock of the terrain, the same way rivers of water carve channels in stone on Earth. The shapes are familiar. The substance is entirely different. Whether any chemistry complex enough to be called life could run on liquid methane rather than liquid water is not known. Water is an exceptional solvent. It dissolves an enormous range of compounds. It supports the movement of ions. It participates directly in the chemical reactions of biology. Liquid methane is not water. Its chemistry is different. The reactions possible in it are different. If any form of biology existed in Titan's hydrocarbon lakes, it would have to run on chemistry that nothing on Earth has found necessary or useful, and it would have to function at temperatures so cold that most familiar chemical reactions slow to almost nothing. Some researchers have sketched out what such chemistry might look like. The kinds of molecules that might serve as membranes, the kinds of reactions that might yield energy in liquid methane. The sketches are theoretical. They remain unverified. But the fact that the question can be asked at all, that the shapes of lakes and rivers and atmosphere are there on another world and filled with a liquid that is not water, is itself a description of how far the habitable zone concept extends and where it stops. The habitable zone was built for water. It was built for liquid water on a rocky surface under the light of a star, because water is what life uses here, and here is the only place where life has been confirmed. It was a reasonable place to start, the best available anchor for the search. But Titan's methane lakes are not outside the zone, because they are inhospitable. They are outside it because the concept was never designed to reach them. The zone's outer edge was defined by the coldest temperature at which water can remain liquid, not the coldest temperature at which any solvent can remain liquid, and not the coldest temperature at which any chemistry might function. Those are different questions, and the habitable zone was not trying to answer them. It was trying to answer a narrower question, and it answered that narrower question well. There is a scale of habitable zones that extends beyond the scale of individual stars. The galaxy itself has a structure, and within that structure, some regions are more favorable for the accumulation of complex chemistry than others. The center of the Milky Way is dense with stars, hundreds of times more densely packed than the region where the solar system sits, and the supernova rate there is correspondingly high. Supernovae release energy sufficient to strip away planetary atmospheres and damage the chemistry of living things across large volumes of space. The outer arms of the galaxy are sparse, low in the heavier elements that rocky planets require, because those elements are built inside stars and released when those stars die. And in the sparse outer arms, there have been fewer stars and fewer stellar deaths, and less time for the chemistry of rock and metal to accumulate. Between the dense center and the sparse outer arms, at a distance of roughly 23,000 light-years from the galactic core, the solar system sits in a region where the supernova rate is tolerable, the supply of heavy elements is sufficient, and the stars are old enough to have had time for complexity to develop. This region is sometimes called the galactic habitable zone. A ring in the galaxy, analogous in its logic to the ring around a star, defined not by temperature and water, but by stellar density, supernova frequency, and the availability of the chemical building blocks for rocky planets. The estimate suggests that roughly 1 in 10 stars in the Milky Way currently falls within this galactic ring. It is a broader, rougher concept than the circumstellar habitable zone. The uncertainties in its boundaries are large, and it is based on fewer direct measurements and more modeling, but the underlying logic is the same. Not all regions of the available space are equally favorable. Some are too hot, some are too sparse, some are too violent, and somewhere in the middle there is a region where the conditions have combined in ways that allow certain kinds of chemistry to persist across time. The galactic habitable zone does not tell any observer where life exists. It tells them where the conditions for rocky planets with liquid water existing long enough for complexity to accumulate are most likely to have arisen. It is a probability distribution spread across 100,000 light years, a quiet background structure in which the local question, whether this particular planet, at this particular distance from its particular star, has liquid water on its surface, is embedded. The two scales do not replace each other. The small question is nested inside the large one, and the large one is nested inside larger ones still. The age of the universe, the time available for stellar generations to enrich the available chemistry, the slow accumulation of complexity across a cosmos that started with nothing more than hydrogen and helium and the energy of the initial expansion. These are not distances the mind can hold at once. The scale from a planetary orbit to a galactic ring to the age of a universe is a scale that slips through familiar measurement and leaves only a residue, the sense that the conditions being discussed are not rare in any simple way, but distributed, spread unevenly across enormous reaches of time and space, in patterns that research is only beginning to map. There is something closer, something that does not require any other star or moon or galaxy. The Earth itself is an example of life existing well outside the conditions the habitable zone concept was designed to describe, and the evidence has been accumulating for decades in laboratories and drill cores and submersible expeditions to places where the surface world cannot reach. Several miles beneath the ground, in the spaces between rock grains, in ancient fractures and porous formations, microbial communities live without sunlight, without oxygen, and without any connection to the surface world above them. They were not known to exist until researchers began drilling deep into old rock formations and analyzing what came back up: the fluid from the depths, the material from the cores, the chemical signatures of metabolism that could not have come from contamination, because no contamination could have penetrated so far into rock laid down so long ago and survived. The organisms living in these deep communities are not like the organisms of the surface. They do not use photosynthesis. They do not eat things that used photosynthesis. They draw their energy from chemical reactions between minerals in the surrounding rock and the water moving slowly through the cracks, reactions that release hydrogen or methane or other compounds that can be used as fuel by cells adapted to run on very little. Their metabolism is so slow that it is almost static by the standards of surface life. Individual cells may require decades to complete processes that a bacterium in a sun-warmed pond finishes in minutes. They are not dormant. They are alive and metabolizing and reproducing, only at a pace so slow that the word still barely captures it. They are more like the rock around them than like anything a surface observer would recognize as quick or living. The review that assembled the full picture of this deep subsurface world estimated that the microbial mass living below the surface of the Earth, in the dark, beyond the reach of any solar energy, constitutes something close to a fifth of all the living matter on the planet. A fifth of Earth's total biomass, by some estimates, lives in conditions that the habitable zone concept cannot describe. No stellar radiation, no surface, no atmosphere in contact with a star, just rock and water and chemical gradients running through the deep. This is not an argument against the habitable zone concept. It is an expansion of the question it was trying to answer. The original concept asked where liquid water could exist on a planetary surface under starlight, and it was asking that question because liquid water on a surface is what could be detected from a great distance by a spacecraft or a telescope measuring reflected light and atmospheric chemistry. The deep subsurface biosphere of the Earth is invisible to any telescope. The ocean of Europa is invisible to any telescope. The roads of Opus, the hydrothermal floor of Enceladus's interior ocean, is invisible to any telescope. The habitable zone was a framework for remote detection, for the instruments that could only measure what reached the surface. What it could not reach was not beyond life, it was beyond the instruments. The concept has not been abandoned. It has been deepened and complicated and returned to with more precise tools and more nuanced questions. The 2013 revision to the zone's boundaries, which updated the underlying physics of atmospheric absorption and shifted the estimated edges by small but meaningful amounts, was not a revision of the underlying logic. It was an improvement in the precision of the same measurement. The framework that asks where water can exist on a rocky planet surface is still the most useful framework available for evaluating the enormous catalog of worlds that distant telescopes detect in transit across their stars. It is not the only framework. It was never meant to be the last word, but it remains the best first filter available for narrowing 100 billion candidates to the ones worth examining more closely. The rocky planet surface is where this kind of life, the only kind of life that has ever been confirmed, began. Whether it began on a surface and later colonized the depths, or whether it began in the depths and later spread upward to the surface, is a question that research has not resolved. The oldest microbial signatures in the geological record are ambiguous enough that both paths remain plausible, but the surface is where the evidence can be read, where the chemistry is exposed to the light, where a distant observer can detect an atmosphere that has been altered by biology. Whatever the deep places hold, the surface is where the story becomes legible from afar. The quiet truth that the habitable zone concept contains is this: liquid water is extraordinarily good at supporting the kind of chemistry that leads to living things. It dissolves minerals and organic compounds. It allows ions to move through solutions in ways that drive reactions. It participates directly in countless biochemical processes, not merely as a medium, but as a reactant, a molecule whose hydrogen and oxygen atoms are incorporated, broken apart, and rebuilt in the machinery of metabolism. It exists across a pressure and temperature range wide enough to be available in many environments. It is among solvents known to exist in significant quantities in the universe, the one most demonstrably associated with chemistry complex enough to reproduce itself. The habitable zone was built around that association, and the association is real. What the habitable zone was not built to capture is the flexibility of the association. Water does not require sunlight. It does not require a surface. It does not require a planet at all. It exists in icy bodies throughout the solar system, in the tails of comets, in molecular clouds between the stars, in the mineral matrices of asteroids. The habitable zone describes where water can persist as a liquid on a rocky surface under starlight, because that is the condition most accessible to distant measurement and most consistent with the kind of life that built the instruments doing the measuring. It is an honest description of a real and important condition. It is not a description of all the conditions under which water can be liquid, or all the conditions under which life might exist. The lake on Enceladus, it is more accurate to call it an ocean, sits in the dark beneath the ice and continues its slow circulation without any concern for what is being mapped above it. The water moves over the hydrothermal vents in the slow mineral warm currents that the tidal flexing drives upward from below. Where the hot water meets the cold, chemical reactions proceed that have been proceeding for as long as the moon has been in its orbit around Saturn. What those reactions have produced across the time available to them is not yet known. What is known is that the conditions for chemistry are present. The water is liquid, the energy is available, the elements are there. The deep rock of the earth holds its slow communities in similar stillness. 4 miles down, in cracks and pores in ancient stone that have not seen the surface in hundreds of millions of years, the cells persist. They do not move quickly, they do not change quickly. They may remain in a single location, metabolizing at a pace too slow for an observer to measure directly, for timescales that dwarf anything familiar from surface ecology. They are not waiting for something, they are simply being, metabolizing, persisting, existing in conditions that would kill every surface organism within minutes, but have sustained them in some form for longer than recognizable animals have existed. The boundary of the habitable zone, the bright ring of warmth around a star, was drawn in a particular moment of scientific history, with the tools available at the time to answer a question that was genuine and important and well formed. It described a physical reality. There is a region around every star where the flux of energy is sufficient to keep water liquid on a rocky surface, and beyond that region, or inside it, the surface temperatures drive the water away in one direction or the other. That is a real boundary. It governs real conditions. It is useful for evaluating real worlds. What it could not anticipate was the depth of the alternatives. It could not anticipate Europa, because Europa's ocean was not confirmed until the late 20th century, decades after the concept was first formalized. It could not anticipate Enceladus, because Enceladus's plumes were not discovered until a spacecraft reached Saturn and flew close enough to sample them. It could not anticipate the depth and scale of Earth's own subsurface biosphere, because drilling technology and microbial detection methods were not capable of reaching and identifying it until recently. The concept was limited by the knowledge available when it was built, in the same way that every scientific framework is limited by what has been measured and confirmed at the time of its construction. The limits are not failures. They are the ordinary frontier of an honest process. Because the frontier has moved. It moves slowly because the questions are hard and the distances are enormous, and the instruments must be built and launched and traveled for years before they arrive at the places being studied. Europa Clipper will reach Jupiter's neighborhood years from now and spend years more making its flybys, and what it returns will be data, measurements, spectra, magnetic field readings that researchers will spend further years interpreting. The answers will not arrive quickly. They will arrive the way all answers to these kinds of questions arrive, slowly, partially, with new uncertainty attending every new measurement, the picture becoming more detailed without ever becoming fully complete. That slow accumulation is not frustrating. It is the character of real inquiry into genuinely difficult questions. The habitable zone concept itself arrived slowly, first proposed in 1959, refined through the 1960s and 1970s, rebuilt with more precise climate models in 1993, recalculated with updated atmospheric data in 2013, and still being revised as new stellar types and new planetary configurations are added to the growing catalog of known worlds. Each revision has made the concept more precise and more useful, and each revision has also revealed something that the previous version could not see. The process has no end in sight. That is what the process is supposed to look like. The organisms in the deep rock of the earth do not know any of this. They do not know the surface exists. They do not know that light falls somewhere above them, or that there are other organisms adapted to live in that light, or that those organisms have developed instruments and questions and frameworks for understanding where life can and cannot be. The deep microbes exist in the slow chemical world that has surrounded them since before the surface looked anything like it does now. They metabolize, they persist. They are, by any reasonable definition, alive. Alive in the dark, in the cold, in the rock, in a world that the concept of the habitable zone was not designed to reach, sustained by chemistry that the concept of the habitable zone was not designed to describe. And in their quiet persistence, they carry a simple and important truth. Life is not fragile. It is not an exception. It is not a delicate thing that requires a precise arrangement of conditions to sustain itself and collapses the moment any of those conditions shift. It is tenacious and various and willing to find the energy available in a given place and run on it, regardless of whether that energy arrives from a star or from a mineral reaction in the wall of a crack in old rock 4 miles underground. The habitable zone describes one set of conditions under which life has demonstrably appeared. It does not describe the limit. The limit, if there is one, is farther than any instrument has yet reached. The icy moon continues its orbit. Jupiter fills a large portion of its sky, or would fill it if anything were there to look. The surface ice is white and crossed with brown lines, and beneath it the ocean moves in the dark, warmed by the flexing of the rock below, carrying in its water the dissolved record of everything the floor has been doing since the moon first formed. The water is patient in the way that very old and enclosed things are patient, not waiting, not moving toward anything, but simply continuing, sustained by forces that do not require any awareness of the fact. The plume on the small white moon rises silently through the ice and disperses into the cold of space. The organic molecules it carries drift outward in the solar wind. The hydrothermal chemistry on the ocean floor below does not pause for this. The reactions proceed in the hot dark, where water meets rock, the same reactions that have been proceeding for as long as the tidal forces have been kneading the interior, releasing hydrogen into a cold ocean that has no season, no tide of its own, no surface lit by any star. Deep in the earth, in the rock, in the slow world below the root of any mountain, the cells go on metabolizing at a pace too slow to watch. The stone around them is ancient. The water in the cracks has been there longer than the current arrangement of continents.